Hello and welcome back to KINE 404, an introduction to epidemiology. My name is Richard Armenta, and in this video we're going to talk about measures of morbidity, specifically focusing on incidence and prevalence. So as we've previously talked about, there are multiple ways to measure disease patterns in the population, including both measures of mortality, which we talked about in our previous lecture, and measures of morbidity, which describe the current health status in a population. So measures of morbidity characterize the number of people who are already ill in a population, which is our prevalence calculation, and the number of people who will become ill over a period of time, which is our incidence calculation. So prevalence, as we just talked about, is the number or proportion of people who have a particular disease, existing plus new cases, out of the total population for a given time period. So for example, this could be something like people living with HIV infection in the United States was 1.2 million people in 2012. Globally, there are over 34 million people living with HIV. So those are prevalence numbers, and those tell us overall about the burden of disease. Incidence, on the other hand, is the number or proportion, depending on the calculation that we're doing, of new cases of a disease in a certain time period. So that could be, for example, in 2012, in the United States, there were 50,000 people that were newly infected with HIV. So this now gives us the number or the proportion of people who got HIV during that time period, which would be from January 1st, 2012 until December 31st, 2012. There are two types of prevalence that we'll talk about, the point prevalence and the period prevalence. The point prevalence is the number of people who have the disease at one point in time. So for example, the number of people who have a cold right now, today, on the day that you're listening to this recording. The period prevalence, on the other hand, is the number of people who have a cold, for instance, or the disease that you're interested in, sometime in the past year or in some time period that you're doing your calculation for. So for example, this could be you wanting to calculate the period prevalence from January 1st, 2019 until March 30th, 2019 for the flu. So that would mean that we would count everybody who has the flu on January 1st, 2019, plus all of the new cases of the flu during that time period would be our period prevalence. So essentially your period prevalence includes existing plus new cases, whereas your point prevalence only includes the existing cases on that day that you're doing your calculation for. Overall, our prevalence calculation is just, as you see here in the formula, the number of people with the disease that you're interested in studying over the total population that you're doing that calculation for. However, there's many issues with prevalence, and depending on the disease, it might be unclear if it's a new or an old case, and we'll give some examples of what that means in a moment. There's no follow-up, so all we know is that somebody has the disease today or on the day that we're doing our calculation, and we don't do any long-term follow-up to see kind of what's going on, how it's developing, how it's progressing, or anything like that. And especially for diseases of long duration, it's difficult to tell if the current environment or behaviors led to the disease. So for example, if we're looking at something like type 2 diabetes, we can look at the prevalence of type 2 diabetes in the United States today on the day that you're listening to the recording. But what we won't know when we're looking at that is whether or not the behaviors that a person's engaging in today are ones that are actually making them or made them at higher risk for developing type 2 diabetes. Because that could be that they change their behaviors as a result of getting diagnosed with type 2 diabetes. It could be that they've had type 2 diabetes for 20 years and their behaviors today are much different than they were 20 years ago when they were diagnosed, or it could mean a whole other host of things. And so the prevalence is really good for telling us the overall burden of disease in our population, but what it doesn't tell us about is the rate of new cases. So essentially, how many people do we expect to get infected with that disease or to get diagnosed with that disease over a certain period of time that we define? That's what we use incidence for. So our incidence describes the rate of development of a disease in a population over a certain period of time. So our incidence is a rate, and it's one of the most important and useful rates that we use in epidemiology and public health, and it contains three elements: the number of new cases, the population at risk, and time, or the period which the cases are occurring that we're doing our calculation for. So if we look at that denominator for our incidence, and I'll show you the formulas in just a moment, one thing that we have to define for our incidence calculation is who is at risk for the disease that we're doing our calculation for. So essentially, who is our population at risk? So what you'll have to think about is that our population at risk, if we're calculating incidence, is people who don't already have the disease, people who aren't already immune to the disease for some reason. So that could be that they already had a vaccination. That could be that they've had the disease and they have lifelong immunity because they've had that disease. That could be because there's some genetic factor that that person has that makes them immune to the disease, or a whole host of other things that might make a person not likely to get that particular disease that you're doing your calculation for. So for example, your population at risk for chickenpox would not include people who had it at the start of their time period, so people who are already infected. It wouldn't include people who have already had it because they're no longer at risk, because once you've had chickenpox, you're not at risk of getting chickenpox again. And it would not include those who have been vaccinated, assuming that our vaccination is 100% effective. And that gets a little bit more complicated, and it's not something we're going to harp on too much in this class. Most of the time, we'll just assume that if a person's vaccinated, that they're no longer at risk for the disease for these calculations. There are two types of incidence that we'll talk about in other lectures to talk about how we actually calculate incidence, and those are our cumulative incidence and our incidence rate. Your cumulative incidence is the number of new cases during the time period that you're doing your calculation for over your total population risk at the start of the observation period. So essentially, you would say, we're going to start calculating our incidence today, and we're going to see over the next month how many people develop the disease. Anybody who doesn't have it or who isn't already immune on the day that we start following, they're going to be at risk and included in our denominator. And then we're going to now count the number of new cases during that time period. And that multiplier that you see is a number that we use to interpret our calculation out of some population size. And that'll make more sense once you see those calculations actually conducted, where you'll see how we use that multiplier to help us interpret the numbers that we're getting for our cumulative incidence and incidence rate. The incidence rate formula that you see here is very similar to our cumulative incidence, except for it tells us the number of new cases during the time period that we're doing our calculation for. But our denominator here is total person time at risk. So person time here is a new concept that we're going to talk about in the next lecture, where we talk about calculating incidence rates, that essentially tells us how much time each person in our population is contributing to being at risk for the disease. So if that doesn't make sense, that's fine. Hopefully once we do some examples, it'll start to make some more sense. And we're still going to use that multiplier that we have here for our incidence rate calculation to make that number more interpretable. So to summarize incidence, incidence focuses on measuring the transition from health to disease. So essentially that what we're trying to examine is that moment when a person gets the disease and determine the rate at which that disease is happening. Our cumulative incidence is the easier measure that we have because it's easy to calculate and understand, because you're just starting out with a population at risk and seeing who develops it. However, it's less accurate when the assumptions of cumulative incidence are not met, and those assumptions will be given in more detail in the next part of this lecture. But essentially, if we talk about the different types of populations, cumulative incidence is really useful when we have a fixed or a closed population, where we're not assuming that people are going to be moving in and out of our population too much. However, most of our populations are dynamic and people are constantly moving in and out, or if we're doing a research study, people might be followed up for different periods of time. So in those instances, our incidence rate becomes a more accurate measure because our person time denominator gives us the amount of time that each person in our study is contributing to risk for the disease. However, that person time denominator is a little bit harder to calculate and understand, especially for the lay public, but it does give us a better and more accurate picture of what that rate of new disease is over time. So if we illustrate the relationship between incidence and prevalence, you can see here we have this jar. In that jar is the number of blue circles. That's the prevalence of disease. So basically, as you have new cases happening, so new people are getting the disease or getting infected or getting diagnosed with diabetes or whatever it is, your prevalence is going to increase. However, as you have people dying from that disease, or you have people who are getting cured from that disease because there's better treatment, then that might make your prevalence decrease. And so your prevalence and incidence are related to each other in that typically as your incidence increases, your prevalence increases, but that also depends on how deadly the disease is and how long the duration of the disease is and whether or not there's good treatment to cure that disease. So why do we need incidence and prevalence? Prevalence tells us the total burden of disease on society. So the higher the prevalence of the disease, the more burden it is because there's more people who have that particular disease. Incidence tells us whether the number of new cases is increasing or decreasing in the population and focuses on transitioning from health to disease. So it tells us that rate of new disease acquisition in our population, and gives us a big clue on whether or not there's an epidemic. So if we all of a sudden see the incidence rate of our disease increasing drastically, that might tell us that we see an epidemic happening in that particular population. If prevalence is a lot higher than our incidence, that means that people are either living a long time with that condition. So that could be something like chronic disease, like back pain, or they have HIV and they're on treatment. So that means that they can live an almost normal lifespan or some other thing. However, if prevalence and incidence are similar to each other, that means that those numbers are very similar. People are either recovering quickly, so that means that there's some kind of cure, the disease doesn't have a long duration or something like that, or they're dying. So that means that people are not living for a long time with that particular disease. And the number of people living with the disease is similar to the number of people who just got it recently. So essentially, if people are either recovering quickly or dying, there's no buildup of prevalent cases, and so your prevalence is not going to increase over time. So we can look at an example using HIV as a really common example for the relationship between incidence and prevalence, where you can see the blue line being the number of people living with HIV, and the gray line being the number of new HIV infections. Our y-axis is the number of infections, and the x-axis is time from 1977 until 2005. And you can see early on from 1977 until about 1985, or about actually 1983, the incidence and prevalence were very similar to each other because we didn't have good treatment for HIV and a lot of people were dying fairly quickly once they were diagnosed. But over time, once we developed a test for HIV and could detect it earlier, and as our treatment has gotten better, our number of new cases of HIV infections and our prevention efforts have also gotten better. Our number of new HIV infections has gradually decreased and or stayed steady over time. However, the number of people living with HIV has increased because we have a buildup of cases because people are living longer and longer with HIV. So this shows us that relationship between incidence and prevalence, where when we have good treatment that people are living a long time with those particular diseases, we have a buildup of prevalent cases, but maybe a steady state of those incident cases. There are many different factors that can increase prevalence and increase incidence. So for example, factors that increase prevalence include things like diseases that have a longer duration, people having a prolonged life without a cure, increased incidence. So if you have an increased incidence, so there's an outbreak of some disease, that means your prevalence might potentially increase if it's not highly deadly. Cases in-migrate, meaning that people from other places or other populations come into the area and they might be bringing disease with them. Non-cases out-migrate, so that might mean that the people in the population who are healthy are leaving that particular area, and so you're leaving a smaller population size, but the same number of people with the disease, increasing your prevalence, or improve diagnosis or reporting. And this one's very common, where we get better testing, we get better early diagnosis of diseases, and so that means people might live longer, or we might be able to find more cases only because we're searching for more cases as well. There's also a number of factors that can decrease prevalence, including a disease that has a short duration, increased case fatality. So if you remember case fatality being one of our measures of mortality, where if more people are dying from that particular disease, you wouldn't have a buildup of prevalent cases. Decreased incidence, meaning that we have a vaccination or better treatment and less transmission from person to person, or whatever that might be, so that whatever that factor could be to decrease the number of new cases. We could have healthy people in-migrating into the population, or sick people out-migrating from the population because maybe they're going to somewhere where there's better treatment, or increased cure rate. So if more people are getting better treatment for that disease, then that means that there's going to be a decreased prevalence of that disease. And so incidence and prevalence are some of the most important measures that we use to describe the distribution of health in our population. And they're ones that you all should become very familiar with throughout the rest of this semester. If you have any questions on the calculations, make sure you're looking at the additional videos on calculating cumulative incidence and incidence rate and on calculating prevalence, and let me know if there's any additional material I can provide. Thank you.